So in this last video, I want to give a few examples, real life examples that these laws tell us about, but I want to review them first. Remember, the zeroth law was just about thermal equilibrium. It allowed us to create a temperature scale and measure temperature. It tells us about temperature being a fundamental property of all matter, which is really important to the other three. The first law is basically the law of conservation of energy. It tells us that energy can't be destroyed, but it can change forms. Talked about the work energy theorem a little bit, that work is done when energy is changing forms. We talked about the difference between work done on the system, between work done by the system, that's an inflow of energy versus an outflow of energy. And then second law of thermodynamics basically says that energy spreads out. It goes from in to out. And heat, this means for heat, it spontaneously flows from hot to cold. That's how we know that. That's why that happens. We also talked about entropy with the second law, that the entropy of the universe and every system in the universe is always increasing. We can do work to get it to go back the other direction, but we can't change the direction of the spontaneous flow. And then the third law of thermodynamics just talks about absolute zero and tells us that we can't ever actually reach that point. All right, so that's what they all mean. And again, it's the first and second law that I want to kind of put together here now in two specific things that we want to talk about, and that's called a heat engine. You need to understand a heat engine. So in a heat engine, let me move me out of the way here. I think this will be okay. I might have to move me again. A heat engine is a device that converts thermal energy into kinetic energy. So draw this schematic in your notes. Basically, what you have is a high temperature reservoir is what we call it. It's just an area of higher temperature. Heat is put into that. We heat up this higher temperature area. And again, we already know that if you heat up an area of high temperature, heat, which is Q, that's what that letter Q is, spontaneously or naturally, automatically flows downhill, so to speak, to the lower temperature reservoir, which is basically anything that's at a lower temperature. And a lot of times we intentionally create something that is at a lower temperature for the heat to flow to. All right, now I'm going to have to move me out of the way. I'm going to put me over here. We know this is the high temperature area here. Flows to the low reservoir. What happens with a heat engine is we're going to actually take advantage of this natural downhill flow and divert some of that energy off to be able to do work in a device that converts that heat energy into kinetic energy. So some of this energy that's flowing downhill gets diverted off. We use some of it to create kinetic energy, but we can't ever actually use all of it. No heat engine is perfectly efficient. And so some of this is going to end up flowing to this low temperature reservoir as well. Again, the point of a heat engine is to create this kinetic energy. And we do that by tapping into the natural downhill flow, sort of like a hydroelectric plant, taking advantage of that natural downhill flow from a waterfall to create some useful stuff like electricity. Now, this schematic doesn't really tell you what's going on. And right now you might be pretty confused. Like, what's a heat engine? Well, an example of a heat engine is a engine itself, a gasoline engine in your car. So there's a really good video that I'll post on Canvas that I want you to watch because it's interesting. Because, most of you, as far as I know, plan on, driving a car in the future, and you ought to know how it works. And so here's the basic steps how an engine works. This is called a cylinder, and there's probably 6 or 8 of these in your car, depending on what you drive. What happens is you have 3 things that are required for a car to run, and that's gas, air, and fire. All right. So we have the first 2. We have air and gasoline coming into the top of this piston. There's a valve that comes down that lets them come in. That's what happens when you press the gas. And there's a spark plug sitting on the top of this. The job of the spark plug, as you might have guessed, is to create a spark. So we suck in this air and fuel mixture. That gets sucked in because at the time, this thing called a piston is driving downward. Piston is connected to the crankshaft, which goes around and around, turns your wheels. So the air fuel mixture is sucked in. Now this whole area is full of air and gasoline. We close one valve. We actually close both valves, and the piston begins to come back up. As it comes back up, it compresses all those gases, and at that moment, at the top of the stroke, we get a spark from the spark plug. That spark is the fire. As you might have guessed, that little arc of electricity ignites the gasoline, creating an explosion, and most importantly, heat. I want you to know that right here, when this spark occurs, that is the high temperature reservoir. That's the source of the heat. That's the hottest point of this entire thing. And from that point, all the heat flows downhill. The heat flows into the air that's mixed in with this gas, and the air rapidly expands as soon as it heats up. That's the point of an explosion. That expansion then forces this piston downward, and it's the forcing of that downward force that drives the piston, that turns the crankshaft. That's called your power stroke. That's where you get your power from, right? And now the piston comes back up, and instead of compressing the gas, we open this valve, and all the exhaust comes out. That's what comes out of your tailpipe. And this happens over and over and over again, thousands of times per minute, right? So this is the basics of a gasoline engine. To put this in context of our high and low temperature reservoir and the work we get out, I want you to understand again, the high temperature part of it is this spark. That's the hottest point. The low temperature is, first of all, is this air, but it's also just everything that's around here. All of the metal heats up, the tailpipe heats up. That heat flows to every part of that engine. But the most important part that we're concerned about that does the work is the air, which expands, which forces the piston down. All of the parts in that engine are doing work to create kinetic energy from heat energy. We're converting this heat energy into the kinetic energy, which eventually turns your wheels. That's the point of this heat engine, to convert this heat energy ultimately into the kinetic energy of the movement of your car. Again, the last and final video will show you a close-up view of that, which is really interesting. But right now, I want to talk to you about the opposite, actually, of a heat engine, and that is a refrigerator or an air conditioner. They both work the same way. Again, it's actually the reverse of a heat engine. You should draw this in your notes as well. All right, so let me move me out of the way again. We still have the high temperature and we still have the low temperature, and heat still flows from high to low. That's the second law of thermodynamics. I can't change that. Heat will always flow from high to low. And the change here is that if we're talking about an air conditioner, the only difference now is that the low temperature reservoir is now inside my house, because in the summertime when I'm running my AC, it might be like 37 degrees Celsius outside, which is around 98 to 99 degrees Fahrenheit, pretty hot in Texas. And it might be 23 degrees Celsius, even if it's 30 degrees Celsius in my house, which is getting pretty warm. It's still cooler than it is outside, and heat always flows from hot to low. So heat always will be flowing into my house. Don't want that. So what we can do with an air conditioner is actually we can remove that heat. I can't change the second law of thermodynamics. I cannot stop this heat flow. It's not possible. But what I can do is take the heat that was deposited inside the house, take the heat that came in, and move it in the reverse direction. I can change directions by putting work in. This brings us back to that second law of thermodynamics, where the natural tendency for things is to go downhill. I can't reverse that flow, but I can take it once it gets down there. I can take it back to the top of the hill by putting work in. So in the previous example with the heat engine, we got work out, right? By taking advantage of that natural flow. Well, now we don't like the natural flow. We want it to go the opposite direction. We have to put work in to get it to go the opposite direction. And that work is done by a device called a compressor in your air conditioner. Let's talk about how an air conditioner works. So again, here's the inside of your house. High temperature outside, low temperature inside. Heat's flowing in. You have your air conditioner, and the work is done by a device called a compressor in your air conditioner. What that does is it compresses this gas called a freon, which then also goes through this thing called an evaporator. You can look up the specifics of this later, but that evaporator basically does this. It makes that gas super duper cold. I'm talking crazy cold, way below the freezing point of water, really cold. And that cold freon gas moves into your house. This is only one part of your air conditioner. This is the one that's outside the house, and this is the one that you see. The one that's inside you don't see as much, and it's either up here in the attic or down in your closet, in a closet in your house. This really, really cold freon gets taken up to the attic or in that closet, and it goes through the second part of your AC system, which is called an evaporator. That really cold gas runs back and forth through these evaporator coils, right? And incorporated with this part of the air conditioner is also a fan. It's a simple blower fan. What that fan does, as you might have guessed, is it draws air from inside the house, and that air has heat in it. Well, where'd that heat come from? Of course, it came from outside the house. That heat flows in automatically. So the air from inside your house and the heat energy that's in it is drawn from this fan, and it goes through these evaporator coils, which again are very cold right now because of that cold freon gas that's flowing through them. As you might have guessed, as the warmer air flows across those coils, it doesn't cool down. I mean, it does decrease its temperature, but what happens is that this is where the second law of thermodynamics takes place. Heat flows automatically from hot to cold, from this warm air into the cool coils. We don't have to do work to make that happen. We had to do work to cool the gasoline, the freon gas down, but we didn't have to do work to make the heat move out of the warm air into the cold coils. That's a natural process. So we don't say that the air cools down. What we say is that we removed the heat from the air. And that's effective because this temperature going into the fan might be 25 degrees Celsius or even hotter. Well, coming out, it could be as low as 10, maybe even cooler, 10 degrees Celsius. Now, that doesn't mean the air inside your house is 10 degrees Celsius. We want to keep it at around 22 to 24. But that 10 degrees is going to help to cool down the rest of the house as that air mixes. Now, we got to complete this process because we took some heat out of the air. Well, where'd it go? Well, it went into that cold gas. Well, as it goes into the cold gas, the temperature of that gas rises because it sucks in that heat. So the temperature of the gas rises, and what we've effectively done is taken the heat from inside the house, we've deposited into this freon gas, which will now come back out to the outside, back out to this AC unit. And there's a fan out there. You might have felt this before. You might have put your hand over the top of it and felt the warm air passing through that fan. Well, what that warm air is, it's the heat that was inside your home that's being taken outside your home, and it's being redirected to the outside, which is where it came from. And now your question might be, well, what's going to happen to the heat now? Well, let's think about that. Heat flows from hot to cold. So yes, that heat actually will just, come back inside the house. And you're like, well, what in the world? That's a total waste. Well, that's really the only option we got. As you might have guessed right now, we're kind of just bailing water here. It's kind of like having a leak in your boat and you're just taking a bucket, taking the water out of the boat. And you might say, well, why don't we plug the leak? Well, the answer is we can't. In a boat, you can. The leak here is the second law of thermodynamics. I can't change that. I can't keep heat from flowing into my house. I can decrease it. I can make it slower by insulating my house, using energy efficient windows, closing the doors, things like that. But the heat's still going to come in. You can't stop that. So the best we can do is simply create a device that's going to take the heat that came in and chuck it back out again. It is going to come back in, but as long as that device runs efficiently, I can at least keep the boat afloat, right? I can at least keep the inside of my house at a comfortable temperature. But this costs money. This person's getting really tired. It takes work. Your air conditioner probably is the most expensive in your entire house in terms of energy use. Now, I said refrigerator. This thing is exactly the same. All you have to do is change the inside of your house to the inside of your refrigerator, and it's the same concept. So that's how the first, second, or really the second and third laws apply to a refrigerator, air conditioner, and a heat engine.